What is an oxidation reduction reaction? Do you know the working principle of a breathalyzer for alcohol? When ethyl alcohol vapor present in the breath comes in contact with the orange-colored acidified potassium dichromate present in the breathalyzer, an oxidation reduction reaction takes place. Here, ethyl alcohol is oxidized to acetic acid, and a dichromate ion is reduced to a chromium ion. The color of the solution changes from orange to green due to the reduction of the orange-colored dichromate ion to the green-colored chromium ion. During the oxidation of ethyl alcohol to acetic acid, the oxidation state of the carbon atom increases from -1 to +3, and electrons are released. Now the dichromate ion absorbs the electrons released during oxidation and is reduced to a chromium ion. Hence, during reduction, the oxidation state of chromium decreases from +6 to +3. In a redox reaction, transfer of electrons takes place from one reactant to another reactant to give new products. Here, the acidified dichromate ion facilitates the oxidation of ethyl alcohol by accepting electrons and is called an oxidizing agent. Ethyl alcohol facilitates the reduction of the dichromate ion by donating electrons and is called a reducing agent. You have completed this activity. Select OK. What is an identification? Click on the 4 chemical reactions that represent a redox reaction. Try again. This is an oxidation reaction, as the sulfur dioxide gas undergoes oxidation to become a hydrogen sulfate cation. Click on the 4 chemical reactions that represent a redox reaction. Right! You still have to search for 3 more chemical reactions that represent a redox reaction. Try again. This is an oxidation reaction, as the zinc atom undergoes oxidation to become a zinc cation. You still have to search for 3 more chemical reactions that represent a right. You still have to search for 2 more chemical reactions that represent a right. You still have to search for 1 more chemical reaction that represent a redox reaction. Correct. Well done! You have successfully selected all the redox reactions. You have completed this activity. Select OK to return. Assess your knowledge. Follow the instructions to perform the assessment. Click on each redox reaction to identify the respective oxidizing and reducing agents. Click on the reactant that undergoes oxidation and acts as a reducing agent. Well done! You have selected the reducing agent. Click on the reactant that undergoes reduction, gains electrons. Well done! You have selected the oxidizing agent. Click on the remaining redox reaction to identify its respective oxidizing and reducing agents. Click on the reactant that undergoes oxidation and acts as a reducing agent. Well done! You have selected the reducing agent. Click on the reactant that undergoes reduction, gains electron, and acts as oxidizing agent. Well done! You have selected the oxidizing agent. Click on the remaining redox reaction to identify. Click on the reactant that undergoes oxidation and acts as a reducing agent. Try again. The oxidation state of the reacting species increases during oxidation. Click on the reactant that undergoes oxidation and acts as a reducing. Well done! You have selected the reducing agent. Click on the reactant that undergoes reduction, gains electron, and acts as oxidizing agent. Well done! You have selected the oxidizing agent. You have completed the assessment. Here is your score. You scored well, and you have completed. I assess your knowledge. Follow the instructions to perform the assessment and how to calculate oxidation numbers. Let's consider the bonding in the covalent compound hydrogen fluoride. If we consider the single bond between the hydrogen and fluorine atoms to be 100% ionic, the more electronegative fluorine gains an electron and acquires a negative charge. The less electronegative hydrogen atom loses an electron and acquires a positive charge. The charges +1 and -1 acquired by hydrogen and fluorine respectively when the bond is considered 100% ionic is called the oxidation number. We follow the rules recommended by IUPAC to determine the oxidation state of atoms in a chemical species. Let's discuss each of these rules. The oxidation state of an element in its free state is 0. The oxidation state of a monoatomic ion is equal to its charge. The oxidation state of fluorine is always -1 when bonded to any element in the periodic table. This is due to it having the highest electronegativity. The oxidation state of the hydrogen atom is +1 in all compounds, except metallic hybrids, where its oxidation state is -1. The oxidation state of oxygen is -2 in all compounds except in peroxides, where it is -1, and in superoxides, where it is -0.5. The oxidation state of alkali metals is +1, and that of alkaline earth metals is +2 in all their compounds. In a neutral compound like sulfur dioxide, the sum of the oxidation states of all the elements is 0. In sulfur dioxide, the sum of the oxidation states of the 2 oxygen atoms and that of the sulfur atom is 0. In a polyatomic ion, the sum of the oxidation states of all atoms is equal to the charge on the ionic compound. For example, in a dichromate ion, the sum of the oxidation state of 7 oxygen atoms and 2 chromium atoms is equal to -2. You have completed this activity. Select OK to return to the menu and continue to the next activity. Assign an oxidation number to each element. Select each chemical species and assign an oxidation number to each atom. Drag the oxidation number of the chlorine into the box provided near the chlorine atom. Well done! You have successfully selected the correct oxidation number for the chlorine atom. Drag the oxidation number of carbon into the box provided near the carbon atom. Select each chemical species and assign an oxidation number to each atom. Drag the oxidation number of the fluorine into the box provided near the fluorine atom. Well done! You have successfully selected the correct oxidation number for the fluorine atom. Drag the oxidation number of the nitrogen into the box provided near the nitrogen atom. Well done! You have successfully selected the oxidation number of the nitrogen atom. Select each chemical species and assign an oxidation number to. Drag the oxidation number of the oxygen into the box provided near the oxygen atom. Well done! You have successfully selected the correct oxidation number for the oxygen atom. Drag the oxidation number of the hydrogen into the box provided near the hydrogen atom. Well done! You have successfully selected the correct oxidation number for the hydrogen atom. From the given options, click on the correct oxidation number of the highlighted carbon atom. Well done! From the given options, click on the correct oxidation number of the highlighted. Try again. Well done! You have selected the correct oxidation number of all the carbon atoms. Select the remaining chemical species and assign an oxidation number to each atom. Drag the oxidation number of the oxygen into the box provided near the oxygen atom. Well done! You have successfully selected the correct oxidation number for the oxygen atom. Drag the oxidation number of carbon into the box provided near the carbon atom. Well done! You have successfully selected the oxidation number of the carbon atom. You have completed this activity. Select OK to assign an oxidation. Assess your knowledge. Follow the instructions to perform the assessment and select each chemical species to assign an oxidation number. Select oxidation number of oxygen to select the correct oxidation number of all the oxygen atoms. Well done! You have successfully selected the correct oxidation number for the oxygen atom. Select Oxidation Number of Hydrogen to select the correct oxidation. Well done! You have successfully selected the correct oxidation number for the hydrogen atom. Select Charge on Chemical Species and select the charge of the molecule to calculate the oxidation number of the sulfur atom. Well done! You have successfully calculated the oxidation. Select the remaining chemical species to assign an oxidation number. Select Oxidation Number of Oxygen to select the correct oxidation number. Well done! You have successfully selected the correct oxidation number for the oxygen atom. Select Charge on Chemical Species and select the charge of the molecule to calculate the oxidation number of the chlorine atom. Well done! You have successfully calculated the oxidation. You have completed the assessment. You scored well and assign an oxidation. Assess your knowledge. Follow the instructions to perform the assessment. Select each chemical species to assign an oxidation number.
Okay, the activity conducted to actually prove redox reaction. The first one was transfer of electron at a distance. And the second one will be the conversion of iron 2 and vice versa, where the substance used in both experiment depends on the role of the substance. Like for example here, iron 2 if oxidized to iron 3, so the agent that is suitable to use will be an oxidizing agent, where the oxidizing agent used in this activity is bromine water. So when you use bromine water, okay, the color change will be for bromine itself. All right, for bromine itself, initial color of bromine is brown. So once reaction takes place, it changes to colorless. Now, what to expect when iron 2 undergoes oxidation to become iron 3 is the green solution becomes brown, right? So that is one of the indication for the process of oxidation taking place in iron 2. Now, further to actually test, or we do a confirmative test to test whether the change is actually iron 3 is using sodium hydroxide, right? So sodium hydroxide, if you get right brown, okay, what you get is iron 3 is brown. Okay, so the brown precipitate indicates the presence of iron 3. So that's what you learned in Form 4 chapter 6 about salt. Now, vice versa means iron 3 can be reduced to iron 2, right, by using a reducing agent. So a reducing agent, all right, the definition of reducing agent is a substance that that reduces another substance but its cells undergo oxidation. So that's the definition of reducing agents. For here we use zinc lah. Now when you add zinc, zinc is always in excess, so we don't really need to measure the quantity of zinc. So once you heat for the chemical process to take place, you will end up with excess zinc where you need to filter. Then after, at the end, you need to do the confirmatory test to test the presence of iron 2. So what you should get is green precipitate lah. You should actually get a green precipitate. Now, there are a few experiments conducted in this part of topic to actually prove redox, right? So redox takes place in most of the chemical reaction. So as we know, the first one was oxidation of iron 2, reduction of iron 3. So the next experiment that we can conduct, all right, to prove that redox takes place, or that reaction is a redox reaction, is what we call as displacement reaction. Now, displacement reaction is actually using a more reactive metal, all right, to displace another metal from its salt solution. Now, what I mean by that is when you have metals, okay, their ability to become a positive ion actually is different. So meaning that there are metals which becomes a positive ion faster or more vigorous. That means vigorous in terms of reactivity. So when we talk about reactivity, we are talking about how fast can a metal turn into a positive ion. So that's why metals are normally referred to as electropositive. So if the metal is reactive, it is more electropositive. Why we say electropositive? Because the tendency to form a positive ion actually increases. All right. Now, here there is a list of metals, right, and its ability, all right, to form positive ion. You don't have to memorize the list because this one will be further discussed in 1.2. All right. 1.2, you will discuss this under the standard electrode potential. So there's no point in memorizing the sequence lah, meaning that the sequence where which metal is more electropositive compared to the other. Now, the concept here is to understand that a more electropositive metal or a more reactive metal will displace another metal. All right, displace another metal from its ion solution or its salt solution. Now, what I mean by displace, okay, if you have, for example, all right, here we have a reaction, okay, taking place between zinc and copper 2. Now, zinc compared to copper 2 or compared to copper as a metal, zinc is more reactive. Now, more reactive or more electropositive lah. Alright, so if it's more reactive, meaning that the tendency to form the positive ion is more, so it's more electropositive. So zinc has the tendency to become a positive ion, okay, by donating 2 electrons. So when it donates the electron, that means zinc undergoes oxidation. Now the 2 electron is donated to copper ion. So copper ion in that sense, during the reaction becomes copper atom. So copper ion, okay, where is copper ion from? Is from the salt solution. So that's why the definition of displacement is a reaction where a more reactive metal displaces, all right, displaces another metal from its salt solution. All right, so the salt solution will contain, all right, a less reactive or less electropositive metal. Now, it's important to identify which metal is more reactive so that you will be able, number one, to identify whether displacement reaction takes place or not. Okay, if let's say the metal used is less electropositive compared to the metal present in the salt solution, So there won't be any displacement reaction. Okay, for example, let's say if I change this experiment, I use copper metal instead of zinc, and I use zinc sulfate or zinc nitrate. So will there be any displacement? So the answer will be no, because copper metal is less electropositive than zinc. So copper metal will not be able to displace, all right, to displace zinc metal from its salt solution. So that is what it means lah, right? So that is displacement reaction. So displacement reaction is also another redox reaction. Okay, then we go to the last one. Okay, the last one is displacement reaction of halogen from its halide solution. Halide means the ion of group 17. So meaning that if you have bromine molecule, so bromine molecule will form bromine ions. So the bromine ions are called, okay, the ions is called halide. Okay, halogen is the molecule, halide is the ions from group 17. Now for group 17 is slightly different in terms of course the terms we use lah. Alright, this is something like displacement, but then we call it as okay, because this is involving non-metal. Alright, so this is involving non-metal. So what we need to understand is both reactions are similar in sense of the concept, but different in terms of the terms we use. Okay, meaning that, okay, here, if let's say you have two substances, all right, you have chlorine, okay, chlorine water, and you have maybe potassium bromide. Now, if chlorine is more electronegative, so I'm using the word electronegative, right? Because chlorine, bromine in group 17, they are non-metal. Non-metal has a tendency to form negative ions. How? By receiving electrons. So if a particular element in group 17 has more tendency to receive electron compared to another atom in the same group, so we say that atom, all right, or that molecule is more electronegative, right? So for here, as well as what we studied in Form 4, is the same. All right, it's the same, meaning that as you go down group 17, the reactivity actually will decrease, okay, because of the size of the atom being increasing going down the group. So when you have a bigger size for non-metal, the tendency to attract electron actually reduces. All right, so meaning that the atom that is located above, okay, the group 17 is more electronegative or more reactive lah. So that particular substance, all right, that particular substance will undergo reduction, all right, because it has to form a negative ion. So forming a negative ion involves receiving electron, so it's reduction. So what is the function? If it undergoes reduction, what's the function of this substance? The function of this substance is an oxidizing agent. So if we think back, okay, we have in group 17, we have fluorine, chlorine, bromine. So bromine is located lower than fluorine and chlorine. Bromine, having a biggest atomic size, will have a low tendency to become a negative ion. So when it has a low tendency to become negative ion compared to chlorine and fluorine, so we can deduce or we can make the conclusion that fluorine, it's a more stronger oxidizing agent, because fluorine compared to bromine and chlorine has a higher tendency, okay, higher tendency to undergo reduction. Alright, to undergo reduction. Why? Because the size is smaller. So it is the ability to receive electron is stronger. So when we talk about being the function of being an agent, so it will become a stronger oxidizing agent. Why? Because it undergoes reduction. So if you have fluorine, chlorine, and bromine, there's no need to memorize. You know bromine is less reactive than chlorine and fluorine in group 17. So that is what you have learned in Form 4. So bring forward what you have learned. Now that you know a new definition, okay, oxidizing agent, reducing agent. So if you know fluorine is more reactive, in a sense that more reactive means to receive electron, the tendency to receive electron, the tendency to undergo reduction. So fluorine will become a stronger oxidizing agent. So when you want to identify whether displacement of halogen takes place or not, okay, this is involving a halogen in a halide solution, meaning that just like displacement of metal, all right, displacement of halogen involves a more reactive or more electronegative halogen. So in this experiment, if you have chlorine in a potassium bromide solution, so chlorine will have the tendency to undergo a reduction. So meaning that why compared to bromine? Because chlorine, like I said, compared to bromine is more reactive. Alright, so more reactive, the tendency to form a negative ion is higher. To receive an electron is higher, right? Thinking back in Form 4. So compared to bromine, chlorine has the tendency to receive electron. So chlorine is an oxidizing agent. So chlorine in that case will oxidize bromide. Alright, bromide, Br minus is bromide to form bromine. So this is called displacement of halogen from its halide solution. So the halide is the ions. So a more electronegative halogen will displace, will displace a less electronegative halogen from its halide solution. Same thing with displacement. Alright, both terms, not to say terms, both concepts are similar. Okay, similar concept. Alright, so that is about displacement of halogen. Now, the last experiment will be on conducting redox reaction for displacement of halogen. Alright, so the experiment will actually use different halide solution and different halogen to actually deduce whether there is any redox reaction or not, right? So that is for the experiment. Now we'll go and watch the last video on balancing redox reaction. All right.
How to balance redox reactions. Assess your how to balance. Let's consider the unbalanced redox reaction for the oxidation of ethyl alcohol to acetic acid in the presence of acidified dichromate ion. Balancing redox reactions by the half reaction method. We follow 6 steps to balance a redox reaction by the half reaction method. In step 1, calculate the oxidation number of all the participating atoms and identify the oxidation and reduction half reactions. The oxidation number of the carbon atom attached to the hydroxyl group in ethyl alcohol is -1. The oxidation number of each chromium atom in the dichromate ion is +6. The oxidation number of the carbon atom in the carboxyl group of acetic acid is +3. The oxidation number of the chromium ion is +3. Hence, the carbon atom in ethyl alcohol undergoes oxidation from -1 to +3 in acetic acid and constitutes the oxidation half reaction. The chromium atom in the dichromate ion undergoes reduction from +6 to +3 in the chromium ion and constitutes the reduction half reaction. In step 2, balance all the atoms except oxygen and hydrogen in both the half reactions. In the oxidation half reaction, there are 2 carbon atoms in both the reactant and product side. Hence, the carbon atom is already balanced. In the reduction half reaction, there are 2 chromium atoms on the reactant side and only 1 chromium atom on the product side. Add 1 more chromium ion to the product side to balance the chromium atom. In step 3, balance the oxygen atoms by adding a suitable number of water molecules. In the oxidation half reaction, the product side is in excess of 1 oxygen atom. Hence, add 1 water molecule on the reactant side to balance oxygen. In the reduction half reaction, the reactant side is in excess of 7 oxygen atoms. Hence, add 7 water molecules on the product side. In step 4, balance the hydrogen atoms by adding a suitable number of hydrogen ions. In the oxidation half reaction, the reactant side is in excess of 4 hydrogen atoms. Hence, add 4 hydrogen ions to the product side to balance hydrogen. In the reduction half reaction, the product side is in excess of 14 hydrogen atoms. Hence, add 14 hydrogen ions on the reactant side to balance hydrogen. In step 5, balance the charge by adding a suitable number of electrons. In the oxidation half reaction, the product side is deficient of 4 electrons. Hence, add 4 electrons on the product side to balance the charge. In the reduction half reaction, the reactant side is deficient of 6 electrons. Hence, add 6 electrons on the reactant side to balance the charge. In step 6, multiply the oxidation half reaction by 3 and the reduction half reaction by 2 to cancel electrons. Now, add both the half reactions to get the final balanced equation. You have completed this activity. Select OK to return to the menu and continue to the next activity.